Hello everyone, myself Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhidayanangar Senior College. In the subject Mathematics, Groups and Coding Theory is very important paper. Now in Groups and Coding Theory, already we have seen the first unit. Now we start with the second unit, that is Groups. Now in groups, we have to study these 3 points: binary operation, second group definition and examples, and third is elementary properties of group. Now first is binary operation. Let G be a non-empty set, then the set G cross G is set of all ordered pairs A, B, where A and B are members of G. A binary operation F on a set G is a function or mapping from G cross G to G. That is, a binary operation on a set G is a function that assigns each ordered pair of elements of G a unique element of G. Now see what is actually a binary operation on some set G. Now first of all, G must be a non-empty set. Then G cross G is nothing but the Cartesian product of G with itself. So it contains all the pairs A, B, where A and B both are members of G. Now, if we define some function f from G cross G to G itself, it means what? We have to apply that function f on every element A, B belonging to G cross G. Then whatever is the element f applied on that A, B is a unique element of G. Then we say that f is a binary operation on that set G. Now, whenever f is some binary operation on set G, G is called underlying set, and that mapping f is called as a binary operation on the set G. In other words, we say that G is closed under f. Now, instead of using f, we use the symbol A star B to denote f applied on that A, B. Now, to clear the concept of binary operation, we see some examples. Addition is a binary operation on the set of integers z. That is, addition means plus. It is defined from z cross z to z. Because if we take any two integers, say a and b, and apply rule of addition on them, that means we apply that function plus on every pair of z cross z, then the resultant element a plus b is again an integer. That is, a star b equal to a plus b is present in z and is unique for all ab belonging to z. Actually, in short, it means what? If you are considering any two integers, then their addition is again an integer and it is a unique element. For example, if I consider 2 and 3, both are integers, then 2 plus 3 is 5, which is again an integer, and that addition element is unique element. If I consider 8 and minus 5, both are integers, and their addition 8 plus minus 5 is 3, which is again an integer, and that element is unique. So in this way, if you consider any pair of integers a and b, then in that case a plus b is again an integer and it is a unique element. So we can say that addition is a binary operation on set of integers. Now, similar to integer set, if we consider Q, the set of rational numbers. What is set of rational numbers? Set of rational numbers, it contains all elements of the type P divided by Q, where P and Q are integers and Q not equal to 0. It means it contains all the fractions. So, all integers are present in rational number set, because if you consider any non-zero integer a, then you can write it as a divided by 1 in the form of fraction. So all integers are rational numbers. Together with all integers, the fractions of the type 1 by 2, 2 by 3, all these are present in rational number set. So if I again define addition on Q, then addition is defined from Q cross Q to Q itself. Why? Because if you consider any two rational numbers, say A and B, and if we add them, then A plus B is again a rational number and it is unique. So addition of two rational numbers is again a unique rational number. And so addition is a binary operation on rational number set. Similar way, addition is a binary operation on real number also. So real number is nothing but set of all rational numbers together with all irrational numbers like root 2, root 3, pi, e, etc. So if you add any two real numbers, then again we get a real number and it is a unique number. So addition is a binary operation on real numbers. So remember, addition is a binary operation on natural number set, then integer set, then rational number set and real number set also. Now see multiplication. So just check, if you multiply any two integers, then what is the answer? So again it is a integer and it is a unique number. So multiplication of two integers is a unique integer. So we can say that multiplication is also a binary operation on Z. Similarly, multiplication is a binary operation on Q, means rational number set, and R means real number set. Now next consider the set M by N R. So this is the set of all M by N matrices with real numbers, real entries. So what is matrix? So matrix is nothing but the arrangement of numbers in rows and columns. So M by N matrices means there are M rows and N columns, and all the entries of matrices are real numbers. So that is the set M by N R. Now, matrix addition is a binary operation on this set, because if we consider any two members of M by N R, means any two matrices, say A and B, in that set, so both are M by N matrices with real entries. Then star means matrix addition is A plus B. So addition of two M by N matrices is again an M by N matrix. So order of resultant matrix is M by N. And as we are adding real number with real number, the resultant addition is again a real number. It means for any two combined real matrices, their addition is again a combined matrix with all real entries, and that matrix is unique. So we can say that matrix addition is a binary operation on M combine R. Now see subtraction. Subtraction is not a binary operation on set n of natural numbers. See, whenever we are saying some operation is not a binary operation on certain set, then in that case it is enough to give one counter example for which it fails. So if I consider 2 and 3 and add them, then 2 plus 3 is then 3 minus 2 is 1, which is a natural number. But if I consider 2 and 3 and I'm doing 2 minus 3, then 2 minus 3 is minus 1, which is not a natural number. That means for every pair of A and B belonging to n, A minus B is not necessarily a natural number. So it holds only if A is greater than B. But for A less than B, A minus B is negative number, which is not present in natural number set. So we can say that subtraction is not a binary operation on n. Here we have considered instead of 2 and 3, 5, 8. Same thing happens. 5 minus 8 is minus 3, which is not a natural number. Now see, here star is defined in quite different way. So an operation star defined on Z as A star B is A plus B minus 2. AB in Z is again a binary operation on Z. First see what is the meaning of this binary operation. It is not our regular addition, subtraction, multiplication, division like that. Here star is defined as A star B is A plus B minus 2. For example, if I consider A is 3 and B is 4, then 3 star 4 will be 3 plus 4 minus 2. So it will be 7 minus 2, which is 5. So in this way, A star B is nothing but first number A plus second number B minus 2 according to definition of star. Now see, for any two integers A and B, A plus B is again an integer. And if we subtract 2 from that integer, then definitely it is an integer. And so this star is a binary operation on Z. So these are some examples. So finally we can say that for any two elements present in that set, if we are applying star on the two elements, then A star B must be an element of that set itself. Then only it is a binary operation. And if you are getting at least one pair AB from that set for which A star B is not present in that set, then it is not a binary operation. Now, these are some remarks from definition. If star is a binary operation on a set G, then first, exactly one element is assigned to each ordered pair of elements of G. That means for any pair AB belonging to G cross G, A star B, that is the only one answer. Then second, the assigned element must belong to the set G. So whatever is the answer of A star B, it is again an element of G. Third, to prove the property, we should prove it for general elements. Then it means we cannot take the elements like 2, 3 if the set is natural number set. Whenever we are proving it in general, then we have to take general elements, arbitrary elements like A, B, X, Y, etc. But to disprove, it is enough to find the elements for which the property does not hold, as we have seen in this example 6. As here the property fails, instead of taking A and B, we have taken specific numbers for which the property fails. Now, after definition of binary operation, actually we have to define what is group. Before defining group, we will see separately the properties in the definition of group. So first is commutative. A binary operation star on a set G is commutative if A star B equal to B star A for all AB in G. See, it means what? So whenever we have to show commutative property, then by taking two general elements A, B from that set G, we have to show whatever is the answer of A star B, it is same as B star A. So just we are reversing the order of A and B. Now, already we have seen that addition is a binary operation on Z, Q, R, N. Now, if you consider any two real numbers A and B, then A plus B is equal to B plus A. So this holds for all AB belonging to R. So addition operation is commutative on R. Then see the subtraction operation. Now subtraction operation is not commutative on R real number set, because if you consider two real numbers A and B, then A minus B, B minus A may be different. For example, if I consider 5, 7 in R, then 5 minus 7 is minus 2 and 7 minus 5 is 2. So 5 minus 7 is not equal to 7 minus 5. It means it is not commutative. Now see, if I consider 5 and 5 itself, then 5 minus 5 is 0, and again changing the order I get 5 minus 5 0. Then in that case I am getting equality. But it is only when A and B are equal. But when A not equal to B, then in that case A minus B and B minus A are different. So as we have seen in the previous remark, subtraction operation is not commutative on real number set. Now, what is associative property? A binary operation star on a set G is associative if A star B star C is equal to A star B star C for all ABC in G. So, whenever you have to show that certain binary operation star is associative on set G, then we have to take three elements A, B, C, which are general elements. Then you can find left hand side, that is A star B star C. First applying definition of star to A and B, and then to answer with C. So that will be our left hand side. Then we find right side. So while finding the right side, first we find the answer of bracket, that is B star C, and then A together with answer in bracket, and then we compare LHS with RHS. If both are equal, then the binary operation star is associative, otherwise not. Or you can start with LHS and then simplifying it. If we are reaching to right side, then also it shows that binary operation star is associative. Now these are very simple examples. Orally we can check whether it is associative or not. The addition operation is associative on R because if we consider any three real numbers A, B, C, then instead of star here it is plus. So A plus B plus C is equal to A plus B plus C. It means while adding the real number, order is not important. Adding A in the addition of B plus C and adding C in the addition of A plus B both are same. So addition operation is associative on R. Similarly, addition operation is associative on Q also. Now, the subtraction operation is not associative on R. Now, as we are saying here, it is not associative. It is enough to give one counter example for which the subtraction operation is not associative. Now, consider some real numbers, say 2, 4, 5. Now, here we find LHS and RHS separately. Now, first see RHS. So, A, B, C are respectively 2, 4, 5. So 2 star 4 star 5 is equal to 2 minus in bracket 4 minus 5. So it will be 2 minus minus 1 which is 3. Now we find left hand side. So ABC are 2, 4, 5. So just putting the values here 2 star 4 star 5. So it is 2 minus 4 minus 5. Now minus 2 minus 5 is minus 7. So one side is 3 and another side is minus 7. So they are unequal. It means A minus in bracket B minus C is not equal to A minus B minus C. So subtraction operation is not associative on R. Similarly, it is not associative on Q also. So whenever we have to find some identity element E of G, then we consider A as any element of G. And then solving the equation A star E equal to A, which is equal to E star A for all A in G, we find the value of E. And then E is nothing but identity element of G. So for identity element actually we get A star E is equal to E star A is equal to A for all A in G. Now see this example. The zero element, that means 0, is the identity element of Z with respect to addition. So whenever we have to find identity element of Z with respect to addition, by definition, if E is an identity element of Z with respect to addition, then star is addition here. So A plus E is equal to E plus A is equal to A. Now in Z addition is commutative. So A plus C is always equal to E plus A. But to find identity element, A plus E is equal to A. So just we can cancel A from both sides. So we get E is equal to 0. So in Z with respect to addition, identity element is the number 0. Similar way, if we want to find the identity element of Z with respect to multiplication, then see, we consider E as an identity element of Z. Then, as star is multiplication in this case, A into E is equal to E into A is equal to A for all A belonging to Z. Again, multiplication is commutative in Z. So, S into E equal to E into A equal to A. So, just either you can compare A into E with A or E into A with A. So, A into E is equal to A now. Now, if A is equal to 0, then in that case 0 into E is equal to 0. So, that holds for any number. But if A is not equal to 0, then in that case A into E is equal to A. Cancelling A on both sides, we get E equal to 1. And when A equal to 0, in that case also 0 multiplied by 1 is equal to 0. Thus, for all real numbers A, we are getting A multiplied by 1 is equal to A. And so, 1 is the identity element of Z with respect to multiplication. Similarly, 1 is identity element of R with respect to multiplication. Now, after getting identity, we can define the inverse of element A. Consider a set G with a binary operation star and identity element E. A is an element of G. An element B in G is said to be inverse of A with respect to star if A star B equal to B star A is equal to E. So to define inverse of some element A, we must have E as an identity element of G. So if E is identity element of G, then B is inverse of A with respect to star. If A star B equal to B star A equal to E. So either solving A star B is identity or B star A equal to identity, we get B as inverse of A. Now note that if B is an inverse of A, then obviously A is an inverse of B. Now in Z with usual addition as a binary operation, minus 2 is inverse of 2 because already we have seen that in Z with respect to addition, 0 is the identity element. So E is 0, and if A is any element of Z, then to find its inverse, we simplify this equation. Now star is addition. So A plus B equal to B plus A is equal to 0. So B is equal to 0 minus A. That means minus A. So for every element A in Z, minus A is its inverse with respect to addition. So in particular, for A equal to 2, minus 2 is its inverse. If I consider minus 5, then 5 is the inverse with respect to addition because minus 5 plus 5 is equal to 0, which is an identity element. But if we consider usual multiplication on Z, then 2 does not have an inverse. See why? Because with usual multiplication on Z, as 1 is the identity element, to find its inverse for every element A in Z, we must get some integer B such that A into B is equal to B into A is equal to 1. But then B will be 1 upon A, and 1 upon A is not necessarily an integer. So in Z, for every element there is no multiplicative inverse. Now, this is one example. The binary operation star is defined on Q as A star B is equal to AB plus 1 AB in Q. Now, we have to check whether it is commutative and associative. Now, already we have seen what is the meaning of commutative and associative operations. Now, for commutativity, we need two elements, and for associativity, we need three elements. So, in all, we require three elements from the set Q. So, we take three general elements A, B, C from Q. Now, to check commutativity, we have to check A star B and B star A are equal or not. Now, first we calculate A star B. Now, what is A star B? By definition, it is AB plus 1. It means simply just we have to do multiplication A into B and then add 1. So A star B is AB plus 1 according to definition of star. Now we cannot simplify it further. So we call this as equation number 1. Now for commutativity, the another side is B star A. Now the first is B and after star there is A. So applying the definition of star again, it will be BA plus 1. Now, A and B both are rational numbers, and in rational numbers, multiplication is commutative. So, BA plus 1 can be written as AB plus 1. Now, see, RHS of equations 1 and 2 both are equal. So, their left hand sides are also equal. That is, A star B equal to B star A for all AB in Q. Thus, the operation star is commutative. Now another part is associativity. Now in associativity we have to check A star in bracket B star C is equal to in bracket A star B star C. So again we find these two sides separately. Now first see A star in bracket B star C. So it is A star. Now by definition B star C is BC plus 1. So this is equal to. Now before star there is A, and after star whatever is the element in the bracket, that is BC plus 1, we consider this as B. So using the definition A star B, it is just product of first and second plus 1. So first element is A, second element is BC plus 1. So their product A into bracket BC plus 1 plus 1. Now we simplify it further because there is no star in that expression. So it is equal to A into BC plus A plus 1. Now call this equation number 3. So this is A star in bracket B star C. Now another side is A star B star C. Now first use the definition of star in bracket A star B. So it is AB plus 1 star C. Now AB plus 1, consider it as first element A and C is nothing but B in our definition. So again product of first with second plus 1. So it will be AB plus 1 into C plus 1. So simplifying it further, it is ABC plus C plus 1. Now compare RHS. Now ABC, they are same. 1 is also same, but here we are getting the term A and here we are getting the term C. So they are not necessarily equal. So from 3 and 4 we can say that A star in bracket B star C is not necessarily equal to A star B star C. So the operation star is not associative. Now, second example, is the operation star defined below a binary operation on Z? A star B is A raised to B, A B in Z. See, how to apply definition to some numbers. For example, here if I consider A as 3 and B as 2, then 3 star 2 is by definition 3 to the power 2. So 3 to the power 2 is 3 square, that is 9. If I consider here 5 and here as 7, then 5 star 7 will be 5 raised to 7. So in this way star is defined. Now to check whether it is a binary operation, we have to take two elements AB in Z. So for AB in Z, just check A star B is A raised to B, whether it is a unique element of Z or not. Now, if both are positive, that means A is positive, B is positive, then that is an element of Z. But problem comes when B is negative integer. For example, if I consider A as 2 and B as minus 3, then 2 star minus 3 is by definition 2 raised to minus 3. So 2 raised to minus 3 is nothing but 1 upon 2 raised to 3, which is 1 by 8. And 1 by 8 is not an integer. So star is not a binary operation on Z. Now one more example. Define a binary operation star on Q star, that is set of non-zero rational numbers as A star B is equal to AB by 2, where A and B both are present in Q star, that is non-zero rational numbers. Now we have to show that star is commutative and associative. Then we have to find identity element and inverse for each element. So to show that it is a commutative operation, we have to take two elements from that set. Now we will take A and B from Q star. Now Q star is set of non-zero rational numbers. So from the entire rational number set, just we are excluding 0. So there are all positive rational numbers with negative rational numbers also. Just 0 is absent in Q star. Now for AB in Q star, we have to show that A star B equal to B star. So that star is commutative. Now what is A star B? It is product of two numbers, that is A into B divided by 2. So that is one side. Now for commutativity, see what is another side, B star A. Now as B is first and A is second element, by definition it is BA divided by 2. But in rational numbers, multiplication is commutative. So BA can be written as AB. So it is AB divided by 2. Now see RHS. RHS are equal. So their LHS are also equal. Hence A star B is equal to B star A. It means star is commutative in Q star. Now, to show that star is associative, we take three elements ABC from Q star. So, ABC are non-zero rational numbers. Now, by definition, we check A star in bracket B star C and A star B star C are equal or not. Now, first consider the left hand side, that is A star in B star C. First, applying the definition of star to BC. A star in bracket. So B star C is by definition BC divided by 2. Again, A is one non-zero rational number and BC by 2 is another national number. So temporarily consider this as B. So again, applying the definition, A multiplied by this second number whole divided by 2. So it is A into BC by 2 whole divided by 2, which is ABC upon 2 into 2, 4. So call this as equation number 3. Now another side is A star B star C. So apply the definition of A star B here. So it is equal to AB by 2 star C. It is equal to AB by 2 star C, which is equal to, again applying definition of star, AB by 2 multiplied by C whole divided by 2. So it is ABC divided by 4. So again, considering the RHS as equal, we get A star B star C is equal to A star B star C. So by definition, star is associative in Q star. Now third is finding the identity element. Suppose E is the identity element in Q star. Then by definition, for any A in Q star, A star E is equal to E star A is equal to A. But in Q star, multiplication is commutative. So A star E and E star A are equal. So we just consider A star E equal to A to find the identity element. Now by definition of star, A star E is AE by 2. So we get AE by 2 is equal to A. Now, as A is not equal to 0, we can cancel A from both sides. That's why instead of Q, here we have considered the set Q star, that is non-zero rational numbers. Otherwise, we can't cancel that A. So as A not equal to 0, cancelling A on both sides, we get E equal to 2. So E is equal to 2 is the identity element in Q star. So if the operation star changes, then in the same set identity may be different. So not necessary always you get identity element as 0 or 1. It depends on star as well as on the set on which star is defined. Now last is finding the inverse for every element. So we consider A as any element of Q star. Suppose that B is inverse of A, then by definition A star B equal to B star A is identity. Again we equate A star B with E because A star B and B star A are equal. Now by definition of star, A star B is AB by 2. So AB by 2 is equal to 2 as we have already calculated E equal to 2. Now to find B, we simplify this. So shift this 2 on right side. So 2 into 2 is 4. And shifting A here, we get B equal to 4 divided by A. Again, we can shift A from left side to right side because it is not equal to 0. So we can divide 4 by A. So inverse of A is 4 by A. It means if A is 1, then the inverse of 1 is 4 by 1, that is 4 in Q star with respect to star. If A is 2, inverse will be 4 by 2, which is 2. So in this way, for any element of Q star, we can find its inverse.